Hello students and welcome back to my channel. In this video today we'll be discussing almost all the aspects of diffraction. Here by aspects I mean class 12th board exam related content, then JEE mains, then NEET exam as well as JEE advanced. All the concepts I'm about to cover. So kindly be patient and try to listen to my lectures, okay? Right. So first thing is that we have to know what is diffraction. Okay. Now in simple terms, we can say that diffraction is nothing but a spreading, okay, or bending. Now suppose you have a light rays, okay, light rays are going in this way, and suppose you have some obstacle here, some opaque object. Then what will happen, then what will happen? Actually light rays are supposed to go this way as per the principle of rectilinear propagation of light. According to principle of rectilinear propagation of light, light must travel in a straight line path. But actually what happens is that you'll find that light enters in this region, which is supposed to be the shadow region. Okay, this region is supposed to be a shadow region, but you will notice that light enters that region, and this region is no longer completely dark. Of course it will be partially dark. Similarly, let us say students, there is an opening here. Okay, there is an opening here, light rays are coming like this. Okay, suppose you place a screen somewhere here, then as per principle of rectilinear propagation of light, what should happen? Light rays must straight away pass undeviated, isn't it? They must pass undeviated. But actually what happens? Here the light rays would bend at the edges or the corners here. It will bend and it will try to enter like this. So actually, strictly speaking, this is supposed to be a geometrically shadow region. Even this is also supposed to be a geometrically shadow region. But light would be present here. Okay. In fact, here you will notice that there are alternate dark and bright patches of light. Even here also you will observe that there are alternate dark and bright patches of light. Same thing here also. So such alternate patches of dark and bright, this thing are known as diffraction fringes. Okay, we have to study all those aspects related to this diffraction. So that means, in short, diffraction would mean what? Diffraction would means spreading of waves because of bending at the edges of obstacles or at the corners or even at the edges of openings. Okay, so because of this phenomena, it will appear as if light is spreading all over. So this phenomena is known as diffraction. I hope that is clear. Now the question is, why do we don't observe diffraction in our day-to-day life? Diffraction of light. Just because the size of the objects, okay, here by size I mean the dimensions of the object or the dimensions of the apertures, that is holes and all, they are not comparable to wavelength of light. As students, wavelength of light, visible light I mean, ranges from 4000 degree angstrom roughly to 8000 degree angstrom. Okay. In fact, if you convert this into micrometer or microns, it will be 0.4 microns to 0.8 microns. Now 1 micron is the width of the hair. Width of the hair is 1 micron. So So that means wavelength of visible light is comparable to the width of each hair. So needless to say that the obstacles, the dimensions of obstacles and the dimensions of different apertures and holes, etc., which we find in our day-to-day life, they are not at all comparable to microns. So that is the reason why we are not able to observe diffraction in case of visible light. Whereas what is the case with sound? We are quite accustomed to to observe the diffraction in sound. For example, suppose your parents are talking in another room of your house. You are sitting in another room. You can clearly hear them. So what is happening actually? The sound waves must be coming out of the room and through the doors or windows, whatever be the openings, they must be reaching you. Even though you may not be connected in a straight manner from your parents, that is, there may not be a direct straight line which can join you and the position of your parent, but still you are able to listen them. That means certainly sound waves are bending at the edges of the doors or windows or ventilators, whatever it is, and hence you are able to hear the sound. So diffraction in sound is a very common phenomenon. Then again, why is diffraction common in sound? Because for the simple reason that the dimensions of doors and windows and ventilators and all, they are comparable to the wavelength of sound. Is it? For example, as we know, audible sound, its frequency, okay, ranges from 20 hertz to 20 kilohertz. And speed of sound, we all know it is approximately 340 meters per second. Speed of sound in air. So accordingly, you can find the wavelength range here. You can find the wavelength range. Okay. V equal to f lambda. So lambda will be V by f. Okay. So accordingly, you will find that it will be of the order of centimeters or even meters. Okay. And that confirms the fact that diffraction in sound is possible. Now one thing let me tell you students, that diffraction is a common phenomena which will be observed in case of each and every wave regardless of its nature. It could be a transverse wave, it could be a longitudinal wave, it could be an electromagnetic wave, I mean non-mechanical wave, or it could be mechanical wave, whatever be the case. Diffraction is a common phenomena. Diffraction is a common phenomena. Okay. Common to all types of waves. Common to all types of waves, regardless of its nature. So now the question is, can we observe diffraction in light? Yes, certainly we can observe diffraction in light, provided if we experimentally set up, okay, if we set up a special kind of arrangement in which the size of the obstacle, the dimensions of the obstacle, or the dimensions of apertures and holes, etc., are comparable to the wavelength of visible light, that is somewhere between 0.4 microns to 0.8 microns. So it's possible to observe diffraction in light as well. That till here it is clear, I hope. Right. Now, once we have understood the meaning of diffraction, then we'll see the types of diffraction. Okay. Now, in light, there are two classes of diffraction. One is known as Fresnel's class of diffraction. Fresnel's class of diffraction, and the other is known as Fraunhofer's class of diffraction. So by now you would have realized that in order to observe diffraction, there has to be a light source and there has to be either an obstacle, as you can see here, the cursor is blinking here, obstacle, or there has to be an opening or aperture, and there has to be a screen where we can observe the diffraction effect. So three things are required: source from which light will be coming, then the object, that is obstacle or the aperture where light is allowed to bend at the corners and peripheries, and the diffraction effect, that is the bending effect, which will be observed on the screen placed a little away from the obstacle or aperture. So three things are required. So based on these, the positions of these different types of diffraction are classified. Now you see, Fresnel, he was a renowned scientist and he used to conduct experiments within the lab. So his light source used to be, okay, some source within the lab, and therefore when the distance between source and the aperture or obstacle, and also the distance between the aperture and the screen are finite, okay, if they are finite, then such kind of a diffraction will be called as a Fresnel's class of diffraction. Whereas Fraunhofer, student, most of the experiments conducted by Fraunhofer were related to sun. That is, in most of the cases, sun was the light source for it. And sun being an object at infinity, light source at infinity, then we can say that here the object should be at infinity. The source should be at infinite distance from the aperture or the obstacle, and automatically, since parallel rays will be incident, they will be focused somewhere at a far off distance. So it follows that even the screen should also be at infinite separation away from the plane of the aperture or the obstacle. Okay. So in most of the cases, he used to take sun as the source. So this way we have two types of diffraction. Now here in our syllabus we will be studying only the Fraunhofer's class of diffraction. Okay, and that too due to a single slit. Okay, because Fraunhofer's diffraction is also related to multi-slit, that is many slits. But here in our syllabus we will be discussing only a single slit. So I hope that is clear. Now the incident rays must be parallel. In other words, the wavefront should be a plane wavefront. We know that when rays are parallel to each other, wavefront will be a plane wavefront. So for that, it's not necessary that the object has to be at infinity in Fraunhofer's class. It can be effectively be kept at infinity. How? It's very simple. Take a source, okay, and place a convex lens such that the source is at the focus of the lens. So automatically light coming from the lens will be parallel. So here the source is effectively at infinity, even though it is not actually at infinity. So this kind of setup is also sometimes used in case of Fraunhofer's class of diffraction. Okay. Then the other thing you have to understand that we cannot place the screen at infinite distance. In that case, if you want the diffraction pattern to be observed on the screen placed at a finite distance, then again we are supposed to use a convex lens such that the plane of the screen is at the focus of the convex lens, so that the light rays get focused here. So that is how experiment is performed. Now we'll be exclusively studying Fraunhofer's class of diffraction. Fraunhofer's class of diffraction. Okay. And that too due to a single slit. Due to a single slit. Okay. So here you have a slit. Slit means just an opening. It is just an opening, and there will be a central line here. You can see central line, and there is a screen here. So this way you have a screen. This is the opening, this is the slit. Okay, let the width of the slit be a. And as I told you, in case of Ramanujan's diffraction, the source is at infinity. So definitely the light waves will be parallel to each other. Okay. And the wavefront must be parallel to the plane of the slits. So I am showing the wavefronts by dotted lines, you can see. Okay. These are the wavefronts. So now here we will be observing the diffraction pattern on the screen here. Okay. In fact, you'll observe that the intensity here is maximum at the midpoint of the screen. You can see this, you can call it as the central line, and this, the position will be known as the central maximum. Position on the screen where maximum intensity is obtained can be called as central maximum, or you can also call it as principal maximum. Okay, intensity is maximum, whereas at other points you'll find intensity keeps fluctuating. There will be a less intensity point, you can call it as dark fringe. Then there's again a bright intensity point, you can call it as a bright fringe, and so on. So it periodically, not periodically students, but in a certain manner, certainly in a certain manner, it varies, the intensity varies. So here we have to understand why does the intensity vary over the screen. That is why diffraction is taking place. That's what we have to understand. So first let us understand the nature of this point. I will call it as O, which is the position of central maximum or principal maximum. Okay. So the explanation given for this is like this. Suppose A, B is the slit and C is the midpoint of the slit. So basically we have divided the slit into two equal portions. One is AC and the other is CD. Okay. Then now if you consider a light, now you see this is AB is basically a wavefront, and as per Huygens wave theory, each point on this wavefront behaves as secondary sources from where secondary wavelets will be arising. Okay, we have already studied. As per Huygens wave theory, each point on the wavefront behaves as a secondary source from where secondary wavelets will be emerging. Now let us consider a secondary wavelet starting from O and also a secondary wavelet starting from B. Since A and B are already in phase, the points A and B are already in phase, being located on the same wavefront, and you can see the distance AO is same as distance BO. So they will be interfering constructively, that is with zero phase difference or zero path difference. So that will result in an enhancement of each other's effect, which in interference we call it as constructive interference, if you recall. Similarly, for any point corresponding to the upper half of the slit AC, there corresponds another point in the lower half equidistant from C. Okay, in other cases it is equidistant from C, where the path difference is zero. So the secondary wavelets interfering here will be interfering in phase, that is without any phase difference. So this way, corresponding to every point in the upper half, there has to be a point in the lower half of the slit where they'll interfere constructively, and hence, they'll get superimposed constructively, and hence they will enhance the effect of each other, thereby increasing the intensity. So that is the reason why we can expect to have a maximum intensity at the center, that is central maximum. I hope that explanation is clear. If that explanation is clear, then we'll draw another diagram to understand the nature of intensity at any other point other than this central maximum. Suppose it could be a D, B, whatever it is. So I'm going to draw another diagram, students. so that you understand it properly. So this is the slit, and this is the wavefront. It's a plane wavefront. This is the central line. Okay, and this is the screen. So this is the central bright fringe. AB is the slit. This is the plane of the slit and also the wavefront. C is the midpoint. Now let us choose a point P where we want to investigate the nature of the point. That is, we want to know the intensity there, whether it is a dark or a bright fringe. Remember, there is no need to show a convex lens, as in most of the books they are showing. Of course, there has to be a convex lens, and this distance should be equal to the focal length of the lens. Only then all the light rays passing to the convex lens will get focused on the focal plane. The screen should be at the focal plane of the convex lens. I hope that is clear. Now, C is the midpoint of this slit. Just join the midpoint of the slit with point P. I'll take this point P as. Now, this angle is theta. Okay. Then, A is the upper edge of the slit, students. Upper edge of the slits. And B is the lower edge of the slits. So, the path difference between the wavelets, secondary wavelets coming from A and B, path difference will be A sin theta. The derivation you can see in the interference topic. Okay. So remember, A and B are the extreme edges of the slit, upper edge and the lower edge of the slit. So we have calculated the path difference between these extreme wavelets, secondary wavelets. Remember, secondary wavelets will be coming from all the points on the wavefront. Okay. Then now let us say that the slit, this delta L is integral multiple of lambda. This explanation was given by Fresnel. Okay, Fresnel was the first person who gave the expression to this. So I am considering this as n lambda. Okay, so I'll take n equal to 1. Okay, n should be integer. N should start from 1, 2, 3, etc., etc. So the first case I am taking n lambda. So therefore, if I take n equal to 1, then I can write delta L equal to 1 lambda. So basically what will happen, you see, since the path difference varies linearly from A to B, okay, so therefore I can say that the path difference between A and C is half of this as compared to the path difference between A and B. So path difference between secondary wavelets emerging from A and C will be equal to half of this, that is lambda by 2. Okay. Now you'll see that corresponding to any point in the upper half, that is AC, there exists a symmetrically located point in the lower half, okay, where the path difference between the interfering waves will be exactly lambda by 2. For example, if you take exactly point A and C, path difference is lambda by 2. So secondary wavelets starting from A and C will cancel each other. Similarly, if you choose any other point, let us say at some distance from A, and you choose another point equidistant from C, I'll name this as, let us say, A dash, and I'll name this as C dash. Then you will find that again they too will have the same path difference lambda by 2, and they will cancel the effect of each other. And finally, secondary wavelets emerging from C and B will cancel each other. In other words, you will see that the overall effect at point P due to the secondary wavelets emerging from AC, complete portion AC, is exactly neutralized or cancelled or nulled by all the secondary wavelets emerging from the lower half of the slit, that is CB. In other words, this has to be a dark point. Okay. Similarly, n could be 2, 3, 4, anything. So that will mark the positions of the first secondary minima, second secondary minima, third secondary minima, and so on. Now they are all known as secondary minima. Why the name secondary is used? Because this, the fringes are not absolutely dark. Some light does exist there. They are not completely dark. Hence, they are not named as primary minimum or something. They are named as secondary minimum. Plural of minimum is minima. So all of them will correspond to secondary minima. Okay. So I'll write this taking different values of n here. Taking different values of n. Remember delta L is a sine theta. The path difference between the secondary wavelets coming from extreme edges. Don't forget that. So let me mark. So this marks the position of secondary minima. Plural of minimum is minima. Okay. Now notice student that if you take n equal to 2, n equal to 2, then you have to subdivide the entire width into 4 equal parts. The first two will cancel each other. For example, this is the slit, let us say. Let us say this is the slit and this is the plane of the slit. You have divided this into 4 equal parts. This is one part, this is the second part, this is the third part, and this is the fourth part. So secondary wavelets emerging from these two parts will cancel the effect of each other. Similarly, the secondary wavelets emerging from the lower two portions will also cancel the effect of each other, thereby resulting in a dark fringe, that is secondary minima. So that will be known as second secondary minima. This position which is shown here is the position corresponding to first secondary minima. Okay. Then similarly, when n will be equal to 3, then if you multiply divide by 2, then you will have 3 multiply divide by 2. I have put n equal to 3 here. Then you will have 6 lambda by 2. So you have to divide this into 6 equal parts. The entire slit has to be divided into 6 equal parts. So they'll cancel the effect of each other through adjacent pairs. For example, the first and second will cancel the effect of each other. Then the third and fourth portion of the slit will cancel the effect of each other, and the fifth and the sixth portion will cancel the effect of each other. So this way you will find that the point is a dark fringe. So therefore I'll just try to show the positions of different dark fringes. This is the central line. This is the central line. Light is coming through this. Okay. Slightly I'll. Yeah, now it's okay. Okay. Here students, you can take the lens. Okay. If you feel disturbed, you may omit the lens, but lens has to be there. Actually, lens is there in the diagram. It is optional whether you want to show it or not. Then now here this is point C. Okay. So if you take this angle as theta 1, okay, then the path difference, that is a sine theta 1, is equal to 1 lambda. This corresponds to the first secondary minimum. Okay. Then again we have angle theta 2 such that here a sine theta 2 is equal to 2 lambda. Then this will correspond to secondary minimum. Similarly, if you have another angle, let us say theta 3, so that a sine theta 3 is equal to 3 lambda, then you have the position corresponding to the third secondary minimum, and so on, students. I hope that is clear. Okay, I hope that is clear. Remember, angles will be very small. For example, suppose this is capital D or F. Okay, let us say this distance is y1. Okay, then you can very clearly see, if you apply tan theta 1 will be equal to y1 by d or f, whatever you want, you can write. Now, usually theta 1 will be very, very small. Okay, probably a fraction of a degree. Then you can take theta 1, tan theta 1 as theta 1 itself, because for small angles we know that tan theta 1 is theta 1. So this theta 1 and also that is equal to sine theta 1. So in that case, this condition can be written as a theta, or I can write like this. From here, in the place of tan theta 1, I'll write y1 by f. In the place of sine theta 1, I'll write lambda by a. So this way you get the linear distance corresponding to the first minima from the central maxima or primary maxima. Similarly, you can calculate the position corresponding to the second secondary minima. Okay, and so on. I hope that makes sense, students. I hope that is clear. Then, now let us consider the condition corresponding to bright fringe other than the central maximum. So what will happen? Suppose, student, you have, let us say, the path difference, this path difference delta L as odd multiple of lambda by 2. Okay, and that odd multiple should start from 3 lambda by 2, not 1 lambda by 2, because already we have 1 lambda. 1 lambda is already more than lambda by 2. So more than lambda, it will be 3 lambda by 2. So let us discuss this. Now suppose, so we are discussing condition of dark fringe, or better to write position corresponding to, we are about to find position corresponding to secondary maxima. Now why it is known as secondary maxima? The word secondary is used because the intensity is far lesser than the primary maximum. Okay, principal maximum, or you can also call it as primary maximum. Intensity as compared to primary maximum is far lesser in the secondary maximum, hence they are named as secondary maximum. So this a sine theta should be odd multiple of lambda by 2. Odd multiple of lambda by 2, where this odd multiple begins from 3, 5, 7 and so on. So they will mark the positions corresponding to the first secondary maxima. Then this will correspond to the position of second secondary maximum, and this will correspond to the position of third secondary maximum, and so on. So what will happen here? See, if it is, let us take n equal to 3 here. Okay. Then, so let a sine theta 1, the first possibility is 3 lambda by 2. Since it is 3 lambda by 2 path difference, we are supposed to subdivide this entire slit into 3 equal parts. 3 equal parts. Okay. So this is one portion, let us say. Then this is another portion. So one portion, and another portion. And as we'll see that the effect due to this will be exactly cancelled by the effect due to this, because after all the average path difference between the waves is lambda by 2, but the effect due to this third portion will be there, even though the effect due to the first two portions will cancel each other, but the effect due to the third portion will be there. So you will have certain intensity there, even though it's not as large as the central maximum or the primary maximum. It will be lesser, but certainly there will be some intensity. So this we call it as secondary maxima, and since this is the first position of the secondary maximum, so it is known as the first secondary maximum. So if I take this as theta 1, then I'll write here that point correspond to A. So this condition has already been written here. Okay. This condition is already written. Okay. Again, if you want to know the position, linear distance from the principal maximum, then there is a length, students. So I have not drawn here. Okay. Then you can see that tan theta 1 from geometry is y1 by f. In this right angle triangle, you can see. So for small angles, you can equate sine theta 1 and tan theta 1. If it is not small, then you have to take the actual values. Okay. So for example, for small angles, sine theta 1 is same as tan theta 1. So tan theta 1 is how much? y1 by f. Sine theta 1 from here it is 3 lambda by 2l. So f goes that side. You have y1 as 3 lambda f by 2l. This is the distance. Okay, here theta 1 is known as the angular position. Angular position corresponding to the first secondary maximum. Angular position corresponding to the first secondary maximum. I hope that is clear. Similarly, if you take instead of 3, if you take 5 here, then that will correspond to the second secondary maximum and so on. Now, between two secondary maxima, you will find one secondary minima, and between two secondary minima, you will find one secondary maxima, alternate. Even though they are not equally spaced, but certainly there will be an alternate dark and bright fringes. So this entire pattern will be known as the diffraction pattern, which is observed on the screen. I hope that is clear. Right. Now let us try to understand some certain other things related to diffraction. Okay, one of the major thing which we have to understand is this. The whatever I am teaching, I am about to teach now, is usually asked in CBSE board exam or even the other state board exams. Okay, class 12 board exam. So before we plunge into this, I'll draw the diagram and then I'll start explaining this. So I'll take three situations here. Okay. Now here you see, students, this is the slit. AB is the slit and this is the central line. Slit width is A. I have taken the slit width much larger than lambda. Okay. If that be the case, then a parallel beam of rays will more or less enter parallelly. Okay. And most probably you cannot see any diffraction fringes here. So you can write here no diffraction fringes. Okay, it's almost straight. In other words, you will find that here light is obeying the principle of rectilinear propagation of light, which states that light travels straight line path. So light always follows straight line path here. So that is what exactly happens here in our day-to-day case. For example, in our day-to-day life, the size of the openings, such as dimensions of doors, windows, ventilators, etc., they are of the order of what, meters. Whereas lambda, just now we discussed, lambda for visible light is of the order of few microns, point. So certainly this is the situation. So we don't observe what, diffraction. Then let us go to this third case when the slit width, the third case I'm discussing, and then I'll come back to the second case. Here slit width is exactly 1 lambda. Okay. Now try to understand, students. Just now we saw that what happens if A is equal to lambda here. We were discussing the position corresponding to secondary minima here. Okay. We were discussing the concept of secondary minimum. So what happens here? If you put this, if you put A sin theta 1 equal to lambda and A equal to lambda, then sin theta 1 will be 1. So theta 1 is 90 degree. That means what? The first minimum itself is 90 degree. 90 degree means almost the light will be like this. That is, this is approximately 90 degree. Same thing here also. This is approximately 90 degrees. So the entire screen is illuminated. The entire screen is illuminated. Okay. In fact, the light which was coming like this has bent almost parallel and emerged parallel to the slits. So the entire region is illuminated. Okay. So again, here also in this case, there are no diffraction fringes. There is no diffraction fringes, even though you cannot observe the fringes, but certainly light has diffracted here, and light has diffracted to such an extent that the entire region is full of light. I mean, the light has spread over the entire possible region. Okay. So usually what happens that since lambda is of the order of few microns, I mean in point 4 to 0.8 micron, if A is also equal to lambda, then this hole can be called as a pinhole. Okay, this can be called as a pinhole. A pinhole is a hole whose dimensions are of the order of wavelength. Then what will happen? Diffraction will be to such an extent that the entire screen will be full of light, even though you cannot observe alternate dark and bright fringes, because the position corresponding to the first minima is at infinity. Just now we saw. Position corresponding to the first minima is infinity, so there is no question of any alternate fringes, dark and bright. Now what we are referring is this case. In all the books and all, even questions which are framed correspond to this case. Okay, where most probably A is maybe say 4 lambda, or A is equal to 5 lambda, or A equal to 6 lambda, and so on, this kind of thing. So you will definitely observe certain bright fringes and dark fringes, diffraction fringes. Okay, and that we have already discussed here. So the thing you have to observe, what CBSE, in the CBSE they ask this, okay? In the CBSE they ask, what will happen if the slit width is reduced gradually from a large value? This is what they'll ask. That is, initial slit width is large, and if you start reducing the slit width, what will be the effect of the diffraction pattern on the screen? So your answer will be, in the beginning when slit width is sufficiently large as compared to the wavelength of light. There is no diffraction effect. In other words, light travels along straight line path. There is no bending. There is no diffraction, means there is no bending at the corners. And simply the image of the slit can be seen almost of the same size. So there is no diffraction. But as you start decreasing the width and over a certain stage, let us say A becomes, let us say 10 lambda or 6 lambda or 8 lambda, whatever it is, then certainly you can see the diffraction pattern, alternate dark and bright fringes there. Okay. And still, if you go on reducing till you have A equal to lambda, then once again there will be no diffraction pattern, even though light will be showing diffraction. You can see light shows complete diffraction. It has spread in the entire space available, and theta 1 itself has gone to 90 degree. I hope that makes sense. So this is a very important question which is asked in CBSE. Okay, student. Then the second question which is asked in CBSE, I mean board exam, not only CBSE students, I am so sorry. It is universally applicable to all kinds of boards, Indian universities. It can be state boards, it can be ICSE, CBSE, whatever it is. The other question which is usually asked is the width of the central maximum. So that we'll understand what is the meaning of width of central maximum, even though we have already derived, but we didn't discuss this. Okay. Now students, see here. See here. In this diagram, you can see this is the point where the intensity was minimum, because this point corresponds to the first secondary minimum, and O corresponds to the central maximum or the primary maximum. So that means that intensity goes on reducing as you move away and away from O till it becomes minimum at this point. That means this entire region corresponds to the central maximum. Central maximum. This entire region corresponds to central maximum. Or you can call this as the width of the central maximum. So here you can see width of the central maximum is 2y1. 2y1. Can you see? That is width. So width of, or spread, you can say, spread of the primary maximum is twice f1, twice y1, where you can see y1 was basically, see here, y1 was basically lambda, f lambda by a, see here, f lambda by a. So I'll note down this as f lambda by a. So for now, let me take this as some distance, let us say d. So you can see that d varies inversely as a. So while reducing the slit width, when slit width was reduced, the spread of the central maximum was increasing. As you notice this, see, initially the central maximum was here itself, then it slightly got spread here, and you can find the central maximum here, and finally in this situation you can see that the entire screen was occupied by the central maximum, because the first minima occurred at infinity in the third case I am telling. So slit width and the width of the central maximum, they are inversely proportional to each other. So this is also very important concept which they ask in the CBSE board exams, or any board exam for that matter. Right, then let us discuss about Fresnel's half period zone, Fresnel's distance, Now Fresnel's distance, first let us understand what is Fresnel's distance, and then we'll derive the formula. ZF. Now students, here we discussed that in the first case, there is no diffraction. In other words, light is exhibiting, principle of rectilinear propagation of light is being followed. In other words, ray optics is applicable here in the first case. Whereas in the second and third case, we concluded that light is showing diffraction, second and third case, and that here wave optics is applicable, because you cannot justify the positions of alternate dark and bright fringes in the otherwise geometrically shadow regions without assuming the fact that light is made up of waves. Okay. So now there must be some demarcation between the first and the remaining cases, second and third case. There must be some demarcation between ray optics and the wave optics concept. Okay. So that is what is related. Resonance distance deals with the demarcation of, okay, or separation between the region of ray optics and the region of wave optics. So let us try to understand. Now suppose you have a slit here. This is the central line here, and this is the screen. Okay. So here, let us say this light is coming like this. Okay, and instead of going straight, it has deviated and it has reached here. So you can see this is slit. Okay, this is a central line. From the central line, the deviation is A. If that be the case, then this distance will be known as the Fresnel's distance. As you can see, Fresnel's distance is the distance where the deviation is equal to the slit width. Okay. So if this has to be y1, so we'll be using this formula. We'll be using the formula for y1. So just now we found that y1 is f lambda by a. So using that, I write y1 is f lambda by a. Then a into a will be a square, and remember f itself is zf. So in the place of f, I write zf, this is lambda. So therefore, Fresnel's distance is a square by lambda. That means if the screen is placed at a distance less than zf, let us say somewhere here, if the screen is placed at a distance less than zf, then certainly you can see that the deviation, okay, the deviation of the light, that is the first secondary minimum, okay, is formed here. So first minimum is formed here. So this deviation is negligible, and we can conclude that light is traveling along straight line path. In other words, ray optics is applicable. Because when do we apply ray optics? When we assume that light is traveling along a straight line path. And when do we assume light traveling in a straight line path? When the deviation is not appreciable. That happens only when this distance is lesser than ZF. But now suppose we place a screen at a distance beyond ZF. Okay, at a distance beyond ZF. Then what will happen? The deviation will be appreciably large, greater than the slit width. In such case, we cannot ignore the diffraction aspect of light. We cannot ignore the bending and hence spreading of light. So then we say that we have to go for wave optics. So wave optics becomes applicable here. So that means Fresnel's diffraction demarcates the two situations in which whether ray optics will be applicable or wave optics will be applicable. And that is given by a square by lambda. I hope that is clear. Now, if this be the situation, based on this we can discuss the limit of resolution and resolving power of different optical instruments, for example, telescope or microscope or even eye also. Okay. Now, suppose student, let us say that first let us try to understand what is the meaning of resolving power and limit of resolution of an optical instrument. Okay. So here, when two objects are very close to each other, or they subtend a very small angle at the observer's eye, it could be because of their actual spacing being less, or it could be because they are far away from the observer's eye. So they'll be subtending a very small angle. Then it's quite possible that the instrument or the eye is not able to detect them as two separate entities, or rather, to the instrument or to the eye, the two objects appear to be the same. The instrument is not able to detect them as distinct or separate. So, the ability of an instrument to detect two objects which subtend a very small angle at the instrument as two separate entities is known as the resolving power, and limit of resolution will be the reciprocal of this. That is, for an instrument it is always preferable that we want a high resolving instrument. In other words, limit of resolution should be less. This should be high and this should be low. Okay. So now what is the Rayleigh's criteria for this? Let us try to understand. Rayleigh's criteria for resolution between two objects, point objects of course. Okay. That means suppose you have a point object. Okay. When seen through the instrument, let us say telescope, then even though this is a point object, but certainly because of diffraction aspects, it will be a it will be just like a disc. Okay. This point corresponding to this corresponds to the central line. Okay. This corresponds to the central line, and this corresponds to the first minimum, secondary minimum, of course. So since this is circular, from the side if you view this circular, so this will also be circular. Okay, this is known as Aries disk. Aries disk. So this will be the radius of Aries disk. Okay, radius of Aries disk is just equivalent to y1 here. Okay, radius of Aries disk is equivalent to y1, but not exactly equal, because here we were considering a plane slit. Okay, but here we are considering a circular slit. So let us pick the formula from here. So I'll be picking the formula for y1 as f lambda by a. So you have to use additional 1.22. That is because of this circular nature of the lens. 1.22 f lambda by a. Okay. So now Rayleigh's criterion for two objects to be just resolved is that the maxima, the central maxima or the principal maxima of one should be at least, okay, formed away from the first minima, first secondary minima of the second object. So that means you have one object here. Let us say O1 is one object and O2 is the other object. When seen through the instrument, let us say telescope or whatever it is. So here, this is the Aries disk for this, and let us say this is the Aries disk for this. Alternate dark and bright things will be there. Okay. Right. So Rayleigh's criteria says that the instrument will be able to resolve these two. That is, it will be able to discriminate between these two as two separate entities if if this falls, okay, if this falls beyond this point. That is, there must be some separation between this. This should be non-zero. This distance shouldn't be non-zero. In the limiting case, let this be exactly incident here. That is, this point you can see could be exactly here. Still, in such case, the two objects will be just resolved. In other words, the separation between the central maxima for the two, separation between the central maxima should be between the two should be greater than or equal to the radius of the Aries disk. This separation, if I take it as some, let us say z, then z should be greater than or equal to radius of the Aries disk. This is the condition. Okay. So what happens? These are the images, remember students. These are the images. So basically, I'll draw the diagram once again to make you understand. Okay. So basically, it's like this. So this is the focal plane. So this is object 1, and you will have different rings here. This is object 2, you will have another different rings here. This is the central line. Okay. So if the object subtend an angle, let us say theta, then the images will also subtend an angle theta. Then this separation, which I have taken as D, should be greater than or equal to R1. So D is how much? F theta. Okay. Because for small angles, with O as the center, you can consider this as an arc length. This D as an arc length. So arc length is equal to radius multiplied by angle subtended to center. And what is R1? Just now we saw R1 is 1.22 F lambda by A. 1.22 F lambda by A. So therefore, you can say theta should be greater than or equal to 1.22 lambda by A. Here theta is known as if theta is equal to 1.22 lambda by A, then the two objects will be just resolved. Then this will be known as the limit of resolution for the telescope. Limit of resolution. Okay. Here what is A, student? A is also known as the linear aperture of the objective. Remember, objective faces the object. So A, or it will be the diameter of the periphery or the boundary of the lens. A is the linear aperture, also known as the diameter of the periphery, means periphery of the objective. Okay, and reciprocal of this will give you the resolving power. So as I again I'll repeat, smaller, lesser the value of theta naught, better is the instrument. This 1.22 has come because of the circular nature of the lens. I hope that is clear, students. All right. So now we'll be able to solve different questions. Okay. So I don't think you require any solving because most of the questions will revolve around this. One next topic, what I am missing is one more topic, that is formula derivation for intensity of diffraction pattern, Fraunhofer's diffraction pattern. That intensity we have to understand. Now basically what happens is this: you have a slit, okay, this is the wavefront, and we have to understand the effect of this. So you have to divide this entire wavefront into small portions, okay, and the amplitude coming due to because of each portion, equally divided portion, you can take it as, let us say, a naught amplitude. Then the superposition of each secondary wavelets emerging from this, superposition of each secondary wavelets emerging from this is the resultant effect. Okay. Now intensity will be proportional to square of amplitude. Please don't be confused with this. This I have written for amplitude. Okay. Now for the sake of simplicity, I am going to take k equal to 1 here. I take k equal to 1. Okay. Without any problem, I can take k equal to 1 here for simplicity. So here, if a naught is the amplitude due to each part, okay, and if, let us say, what you call delta is the phase difference here between the interfering waves, then we can see the resultant intensity will be something like this. See, so first we have a1, a naught due to this, the effect of this part here is like this. Then from here we have to take another a naught at an angle delta. Then from here we have to take another a naught. Then from here we have to take another a naught, and so on. Okay. So this will be the resultant from here to here, resultant amplitude. So we have to understand this. Resultant amplitude is the vector sum of the amplitudes due to different waves, different unit. So the entire slit has been subdivided into different portions. The amplitude corresponding to each portion I have taken as a naught. Okay. If suppose if I divide this into n number, then I'll say, and if the effect a naught will be equal to the total amplitude, okay, total amplitude due to the entire slit upon n. Now we can have, now what is delta? Delta is total phase difference between the interfering waves, secondary wavelets starting from A and B. Okay, total if I take as phi divided by n. What is phi? Phi is the phase difference between the secondary wavelets emerging from the extreme ends of the slits A and B. So I have divided into n parts. So phi is the phase difference between adjacent secondary wavelets interfering at this point. Okay. So basically, The total phase difference from here to here is actually phi. That is, angle between this and this will be actually a phi. Now, second thing, if O be the center of the circle, then you will find that all these vertices of this vectors will lie on a circle. Not this is not necessarily the diameter, but certainly it will lie on. So I'll redraw the diagram, students, so that you understand better. So let me draw this. So this is the okay. So starting from here, this is the center, and this is A naught. This again A naught. Sorry, I just draw it. This again A naught, and so on. Okay, this again A naught. Just I have taken 4 to make you understand. Okay, now you see this angle between this and this. I'm sorry, I had to take tangential here. So this will also be phi total angle. Here phi is the phase difference between the extreme edges of the slit. Phi. So this resultant amplitude, if you drop a perpendicular here, okay, I'll take this as PQ, then A total is equal to twice PM, twice of this, because these are two congruent triangles, and this each angle will be 5 by 2. Here also it is 5 by 2. And if I take R as the radius, then this will be R sine 5 by 2. Okay. In this right angle triangle, this is perpendicular. Perpendicular is equal to hypotenuse into sine. Okay. Now R can be expressed in terms of A naught. Okay. So here once again O, this R, this R. Now each side will be subtending an angle 5 by n, because there are n sides. So if I divide this, it will be this is A naught. This angle will be 5 by 2n. So in this right angled triangle, I can write sine of 5 by 2n is equal to perpendicular, that is A naught by 2 upon R, 5 by 2n. So this I'll write it here. In the place of 2R I can write A naught upon sine 5 by 2n into sine 5 by 2. So therefore, since n is large, therefore what I can write is 5 by 2n is small, and for small angles sine can be equated to the angle itself. So sine 5 by 2n will be equal to 5 by 2n itself. In that case, we have amplitude as A naught upon 5 by 2n into sine phi by 2. So finally you have n a naught into sine of phi by 2 upon phi by 2. Now remember students, what is a naught into n from here? At, that is total amplitude. So I'll write this as a total into sine phi by 2 upon phi by 2. Okay. Now, what is a total? The total amplitude due to all the waves put together. So therefore now can I write intensity, which I took as square of amplitude. I can write I as total intensity. Total intensity, I'll take it as I naught into sine square phi by 2 upon phi by 2. This is the formula for intensity. Again, what is phi? Again, I'll repeat, phi is the phase difference between the extreme waves. So if I take we have already calculated this in the previous videos, that phi is path difference by lambda into 2 pi. What is the path difference? It is a sine theta. Okay, if I have to draw this is a central line and this angle is theta, and a is the slit width. Then I can write like this. So therefore 5 by 2 will be how much? A sine theta into pi by lambda. Okay, if I write it as alpha, then this expression can be written as I is equal to I naught sine square alpha or sine alpha by alpha whole square. In foreign books, you will find that this is written as sine c alpha square, where sine c x would mean sine x upon x. This is the formula for the intensity. I naught is the intensity of the central maximum. I naught is the intensity of the central maximum. Got it? Primary maximum you can call it. Now, depending on the values of alpha, when you substitute for different values of alpha corresponding to maximum or minimum, you will get the different results. So here we are interested in the intensities of maxima and minima. So let us first find intensity of secondary minima. Okay. So certainly I must be negligibly small. So that means we have sine alpha equal to 0. From this equation you can see. Okay. What is, if sine alpha is 0, that means alpha should be 0. And what is alpha? Here you can see alpha is this, a sine theta pi by lambda. A sine theta into pi by lambda. Okay. Now excluding theta equal to 0, okay, you have to exclude this because that will correspond to a central maximum and we are investigating the positions corresponding to secondary minimum. So please don't take this. So in that case, if this is 0, okay, that means what? If this is 0, that means these must be, sorry, here alpha must be integral multiple of pi other than 0. We should not take 0. So this should be integral multiple of pi. Remember, n starts from 1, 2, etc. Okay. So pi gets cancelled. We have sine theta as n lambda by a, or a sine theta is equal to n lambda. This was the condition. Remember, a sine theta is n lambda. You can see in the other videos. Okay. So this was the condition. Then we want to know the intensity. So intensities are practically 0, negligibly small. Then we want to know the intensity and positions of secondary maxima. Intensities and angular positions corresponding to secondary maxima. So that in that case, sine has to be maximum here. Sine has to be maximum. So if sine has to be maximum here, then that maximum value could be 1. So sine alpha should be maximum here. Okay, can you see, students? This is the, so here sine alpha should be maximum. So intensity should be maximum means sine alpha should be maximum mod. So sine alpha could be plus or minus 1. Okay, and so when do we have sine alpha equal to plus or minus 1? When alpha is equal to odd multiple of pi by 2. And what is alpha? Alpha is this, a sine theta pi by lambda. A sine theta pi by lambda is equal to 2n plus 1 into pi by 2. So cancelling out pi on both sides, we have sine theta, a sine theta is odd multiple into lambda by lambda, that's all, lambda by 2. So this was the condition we already obtained, if you remember, for right hinge. Okay, a sine theta is odd multiple of lambda by 2, where 2n plus 1 starts from 3. Okay, please don't substitute 1. 1 is excluded here. 1 is excluded. Okay. Now, if we can substitute this, okay, these values, then we can certainly have the intensities here. We can certainly have the intensities. So let us find the intensities corresponding to the first secondary minima, second secondary minima, and so on. Okay, so I'll borrow this expression, students. Here, I equal to I naught, sine alpha by alpha whole square. So from I is equal to I naught sine alpha upon alpha whole square, for I to be maximum, okay, sine alpha should be maximum mod of sine alpha, because it is square here. So sine alpha should be plus or minus 1, which implies alpha is odd multiple of pi by 2. Odd multiple of pi by 2. Okay. So that means for the first secondary minimum, sorry, first secondary maximum, this odd multiple should be 3, and for the secondary maximum, this odd multiple must be 5. So therefore intensity corresponding to this will be I naught into 1 upon alpha. Alpha is 3 pi by 2 whole square. So this will be 4 I naught upon 9 pi square, which is approximately I naught upon 22, which is around 0.045, somewhere around this, I guess. Let me confirm this so that you don't have any problem later. So this will be 1 divided by 22. Yes, 0.045. Then coming to I2, for this we have I naught into 1 upon 5 pi by 2 whole square, which will be 4 I naught upon 25 pi square, which is around I2 upon I naught by 62.5 approx. So this is around 0.016 if I am not wrong. Let me check. Yes. Okay. So therefore, if I naught is the intensity of maximum, first central maximum, then the intensity of the first secondary maximum will be this, and intensity of secondary maximum will be this. So you can see they are very, very small. So therefore, if I were to draw the diagram here, then the intensity distribution will be something like this. This is the central line. This is the central line. I am not showing the slit and all. So if this is the intensity corresponding to the central maximum, then the intensity corresponding to the different minima will be like this. Okay, this is I naught, then this will be I naught by approximately 22, and this is I naught by 62.5. This is the intensity distribution of diffraction pattern on the as observed on the screen. Okay, intensity distribution as observed on the screen. Okay, so I hope this should be enough for you, students. Okay, this must be enough for you. I hope that's all in this video. Thank you so much for watching.